Alright, hello everyone, welcome to another video on machine learning. In this video, let us begin by talking a bit about how leaders are chosen in a democratic country. So, if we have to choose a leader in a democratic country, we do not go to one single individual, no matter how important that individual might be. We do not go to him or her and ask, who do you want your leader to be, and make that person, this whoever this important individual chooses, we do not make that person our leader. Instead, what we do is we have election, and on the day of the election, all the eligible voters, lots of people go to a polling booth and cast their vote, and then whoever candidates gets the highest number of vote, that candidate is chosen as the leader. Alright, this is in contrast to what we have been doing in classification or regression till now. Alright, up to this point, whenever we have to do classification, we used only one model, one machine learning model that we have created either using KNN or naive Bayes or decision tree learning. Or there are other algorithms that we are going to see further down the line, like logistic regression, SVM. So we have, up to this point, we have created only one model, and then we ask this model to tell us what is the class of some unknown data. When we give the model some unknown data to do prediction on that unknown data. So this model is going to give us a class. This model is going to do classification for us. Now, if the model does correct classification, that is well and good, but this single model may end up making error. Alright, this is in contrast to what happens in a democratic country. In a using this democratic principle, if we do classification, then what we are going to have is we are going to have, instead of one model, we will have multiple models. Alright, and then these multiple models are going to give us multiple output on the unknown data. When we get some unknown data that we want to classify, or we want some regression output on this unknown data, then we will give this unknown data to all these multiple models that we would create if we want to do our prediction using this democratic principle. Then all these different models are going to give us different output, right? And then our final output is going to be a combination, a ensemble of all these different models, different output. So this is the basis behind today's video. In today's video, we are going to look at something called ensemble method that essentially combines multiple models so that we will be able to do prediction. Alright. Now, this video is the third and the last video on this series of video in which our focus is on decision tree learning. So we are going to see elements of decision tree learning in this video as well, and this is the last video in which we are going to be looking at elements of decision tree learning. So without further ado, let us begin today's video. The first thing, what is ensemble method? Ensemble methods are meta-algorithms. These are not algorithms per se. So algorithms, we have studied a few of them. We have studied algorithms like KNN, naive Bayes, decision tree, ID3 algorithm. Ensemble methods themselves are not algorithms. Okay, they are going to use algorithm behind the scene, algorithms like KNN or naive Bayes or decision tree behind the scene, in order to create an ensemble. So it's kind of like a meta algorithm that uses other algorithms behind the scene. Alright, so these are meta algorithms that combine several machine learning techniques, okay, in order to do prediction. So we are going to create one predictive model. This ensemble method is going to be one predictive model. It is going to give us one prediction, but in order to do that, it is going to use several machine learning techniques. Alright, so the basic idea behind what we are going to do is ensemble method is this. Instead of creating one machine learning model that gives us our output, we are going to have several machine learning models. Say machine learning model 1, machine learning model 2, and say machine learning model 3. Alright, say we are going to create three different machine learning models, and say these three machine learning models, one we have created using say KNN, another using naive Bayes, and another using decision tree learning, and these are all trained on data to give us this classification. Given an unknown image of a cat or a dog, these machine learning models have to tell us whether the image is of a cat or a dog. Say the first model, given an unknown image, the first model tells us that the image is the image of a cat. The second model tells us that the image is the image of a dog. And the third model tells us that it is the image of a cat. So what do we see here? We see that cat has got two classes, two votes, and dog has got one vote. Therefore, my ensemble method, this ensemble model that I have created using these three different machine learning model, alright, that is going to give the output that the unknown image is the image of a cat. So my final prediction, my final classification is going to be cat. Alright, and this is the idea behind today's video, and this is how voting works in ensemble method. Now, in all the cases, things are not going to be so easy. We are going to have more features in ensemble method that we are going to look at in this video. But essentially, there are three different techniques to do ensemble method. One is bagging. In bagging, we are trying to decrease our testing error. All right. So variance means testing error, and decrease variance means we are trying to decrease testing error when we are trying to do bagging. Another is boosting. Bias means training error. Here we are trying to, in boosting techniques, we are trying to decrease the training error. And then there is an entirely different technique known as stacking, which is different from bagging and boosting, and here the focus is mainly on improving the prediction. Alright, so this is what it is. Ensemble method at a very high level is going to combine several machine learning techniques. So here I have three different techniques that I am going to combine, and then we are going to have all these different techniques, all these models that we create. They are going to give us different output, and our final output that we will give, for example, here we are giving the output class cat, is going to be a combination of the output of all these models. So how are we going to combine them? That is going to depend on several things, right? We will talk about those several things in this video, and this is ensemble method. Now there are different perspectives of looking at how to classify these ensemble methods. So the first perspective is this: uh, whether the ensemble method is a sequential ensemble or a parallel ensemble. In sequential ensemble, what happens is we are first going to create one machine learning model. Alright, and then we are going to see what is the performance of this machine learning model, how good is this machine learning model performing, and based on the performance of this first machine learning model, we are going to go ahead and create the second machine learning model, and then we are going to look at the performance of the second machine learning model, and based on the performance of the second model, we are going to go ahead and create the third machine learning model, and so on. Alright, so things are working on a sequence. The first model influences how the second model is going to be created. The second model influences how the third model is going to be created. So there is a dependency among all these different models that we are going to create in sequential ensemble. Alright, so in sequential ensemble, base models are generated sequentially. Now base learners are this. This is my ensemble. All these are called base learners. The smaller models that we are going to use, the models that are going to be there inside my ensemble, the algorithm that we use to create this model are called base learners. Alright. Now compare that to parallel ensemble. Alright. In parallel ensemble, what is going to happen is we are going to have, again we are going to have multiple machine learning model, but then we are going to create all of this model in parallel. So the machine learning model 1 that I am going to create is not going to influence any other model or is not going to be influenced by any other model. So each model that I create is going to be independent of the other models. It's not going to be influenced by any other model. It is not going to influence any other model. So these models will be generated in parallel. Alright. So base learners are generated in parallel. Alright. There is no dependency among all these models that we are going to create in parallel ensemble. Now we are going to look at two algorithms. One is random forest. This is an algorithm for parallel ensemble, and one is AdaBoost. This is an algorithm that does sequential ensemble. Alright, so this is one perspective of trying to classify ensemble method. Another perspective is this: whether the models that we are going to create is homogeneous or heterogeneous. Homogeneous means of the same type. This means this. Say we are going to create three models, and all the three models we are going to train using the same algorithm, same KNN. So I am going to apply KNN on the first model, I am going to apply KNN on the second model, and I am going to apply KNN on the third model. Alright, if I do this, then this is called homogeneous ensemble. So in homogeneous ensemble, this is what happens. Most ensemble method uses single base learning algorithm to produce homogeneous base learner. So a single machine learning algorithm is going to be used. In this example that I showed you, we are using KNN. Alright, a single base learning algorithm is used to produce homogeneous base learner. So homogeneous base learner means base learner of the same type. Alright, so learners are of the same type. So if learners are of the same type, those are called homogeneous ensemble. Now contrast this to this other example. So instead of using only one algorithm behind the scene, say my first model is trained on KNN like before. My second model is trained on naive Bayes, and my third model is trained on decision tree. Here I have different base learners working behind the scene. My ensemble contains three models that you can see. This is machine learning model 1, this is model 2, and this is model 3. Now I have three models that are working behind the scene in my ensemble. My ensemble contains three models, and all three of them are trained on different uh, using different base learners, different algorithms. Alright. So if I train my models that I am going to create using different algorithm, then I have this something called heterogeneous ensemble. Alright. So heterogeneous means of different type. Homogeneous means of the same type. So this is what it is. Alright. Now a bit more before we look at this algorithm, let us look at what bagging means. So we said there are three techniques to do ensemble. One was bagging, one was boosting, and one was stacking. So let us start by looking at what bagging means. Bagging stands for bootstrap aggregation. I will soon explain what bootstrap means. Uh, Now, the reason we use bagging is because we want to decrease training error. Testing error. Now, one model, if we create one model, then what may happen is that model is going to have some amount of testing error, right? So this is my model 1, this is my model 2, and so on. I will have up to say n number of models. Now how do I go ahead and train this model? Okay. Now if I have one model, I will have some amount of testing error. Alright. But if I use multiple model, then the testing error is going to decrease. How is the testing error going to decrease? This say there is a certain unknown data. Alright, and we feed this unknown data into all this n number of machine learning model. We ask this all this n number of models that we have trained. We ask all of them to do prediction on this unknown data. Alright, say classification. Now, my machine learning model 1, say it gives correct output. Model 2, say it gives incorrect output. Model n, say it gives correct output. Say in this way, say 60% of my models give correct output and 40% of my models give incorrect output. Alright. So if I ultimately end up doing voting, then what I'm going to see is that most of my models are voting for the correct class. Therefore, I am going to end up with correct output. Right. So I am going to predict the correct prediction. So this is the basic idea behind bagging. Alright. Now here is the thing. How do I go ahead and train all these different machine learning models? This is what I do. I am going to have this data set on which I am going to do this training. Right? I am going to have say n number of rows and m number of features. Alright. Now I am going to, from this large data set, this is my original data set. From my original data set, I am going to create smaller data set. So I am going to create n models and therefore I am going to create n small data sets. Okay, this is my data set. This is my small data set 1. This is my small data set 2. This is my small data set n. Alright, in this way I am going to create small data sets. Now how do I create small data sets? Before I go ahead and create small data sets, before I start training my ensemble method, because before I start training my ensemble, I have to decide something. I have to decide what is the maximum number of rows, the number of samples that I am going to take into my small data set. Say I have decided that I am going to take 80% of my rows into my small data set. Then what I am going to do, from my original data set, I am going to randomly pick 80% of the rows and bring them to this data set. Alright, so that is how I create data set 1. Then I'm going to go back to my original data set and again I'm going to choose 80% of the rows randomly and then put them in this data set. And I'm going to keep on doing this repeatedly. Ultimately, I'm going to put 80% of my rows into this data set. Now this is very important. Say I have some ith row. Alright. Now say in my model 2, I have chosen this row. Alright. Now once I have chosen this row, I am not going to remove this from my original data set. Alright. So say in some model I have chosen this row randomly. In some other model data set that I am creating, in this data set, creating this data set, I had chosen this row. Alright. Now when creating this data set, I may choose this row again. Now once I have chosen this row to be part of one small data set, I am not going to remove this row. Alright. So this is very important. The fact that I have created this data set from this original data set is independent of how I create this data set. Alright. So I may choose this row to be part of this data set. That does not mean that once I have chosen this row, the probability that I choose this row again to be a part of this data set is not going to be influenced. Alright. Now if in my first data set, if I choose a row, okay, and I remove that row from my original data set, from this data set, then what is going to happen? My second data set that I am going to create is going to be influenced by the first data set. That is not going to happen. Alright. So any particular row, when I choose it once, does not mean I'm going to remove it. I may choose it again to be part of some other data set. Alright, so that is what it is. That is what it says in this paragraph. So we are going to train m different. I am writing trees here. I have written trees here, should have written model. We are going to train m different models on different subset of the data. Alright, so what is the size of the subset? We have decided that the size of the subset is 80%. So I am going to randomly choose 80% of the data from my original data set. Say my original data set had 100 rows, therefore this small data set 1 is going to contain 80 rows. Small data set 2 is going to contain 80 rows. Small data set n is going to contain 80 rows. Alright, so this is what it is. Now we will train m different models on different subset of the data. How are we going to choose this different subset of the data? These are going to be chosen randomly with replacement. Alright, with replacement means once I have chosen a row, I am not going to remove it. Alright, this row is going to stay. So yeah, that is what it is. This technique, choosing rows randomly with replacement, is called bootstrap sampling. Alright, so this is what I am going to do. I am going to create m different models that I am going to train on this n different models that we are going to train on this n different small data sets that we have created, and that is how we are going to generate this m different models, and the output that we are going to give is going to be computed on the ensemble on this n different models. So when we have some unknown data, all these n different models that we have trained, we are going to give the unknown data to all these n different models. These n different models are going to give us n different output, and our final output is going to be a combination of this n different output that these n different models have given. Alright, now how are we going to compute the final output? So for aggregating the output of all these base learner, all these models in our ensemble, so to aggregate the output, what we are going to do is, in case of classification, we are going to do voting. Alright, and in case of regression, we are going to do averaging. Alright, so we have seen how voting would work. Say I have three model, two models says cat and one model says dog. So cat is the class that has the highest number of votes. So cat would be my final output. And in case of regression, we are going to do averaging. Say I have three models, model 1, model 2 and model 3. I have three models. Alright, first model says my regression output is 0.5. Second model says regression output is 0.7. And third model says regression output is 0.6. So I am going to take the average of all this regression output of all these different models, and the average is 0.6. Therefore my predicted regression output is going to be 0.6. Alright, so this is how this aggregation is going to take place in case of regression. Alright, now one very popular technique to do bagging is random forest. We will soon talk about random forest, but before doing so, let me tell you one more thing in bagging that I did not write in this slide. Alright, now alright, we have discussed that we are going to randomly choose some subset of the data, right? So we have talked about randomly choosing 80% of the rows from the data set. Now there is one more thing that I can do, that I should do, is we are going to randomly choose different number of features as well. say I have m number of features, I am not going to choose all the features when I create the small data set. So this is my small data set 1. Alright, I have chosen 80% of the rows. Now all the features that I am going to choose are not all of them. So not only do I choose my rows randomly, I am also going to choose my features randomly. So there were say m number of features, I am going to choose 70% of them. Alright, so if I had 100 features, say I had 100 columns, I am going to randomly choose 70 of the columns in my small data set. Alright, so not only do I make this random choice when choosing these rows of data, I am going to make this random choice in choosing the column of the data as well. Alright, and once again we are going to do this with replacement. Once I have chosen some column, alright, I may choose that column again. Okay, now yeah, this is what it is. So randomly choose rows and randomly choose column. How many rows are we choosing here? I have decided to choose 80% of the rows. How many columns are we choosing? I have decided to choose 70% of the column. Alright. Now let us go ahead and look at a scikit-learn code to do bagging. This is a scikit-learn code to do bagging. Essentially we make this bagging classifier using only one line of code. This classifier is going to do what? It is going to use KNN. Alright, all these models are going to be created using KNN. How many rows are we going to choose? We are going to randomly choose 50% of the rows. How many features are we going to choose? We are going to choose 50% of the features. Right. So that means, say, I have this iris data set. Iris data set has sepal length, sepal width, petal length, petal width, and species. Say this is my row 1, row 2, row 3, row 4, row 5, row 6. Say I have 6 rows in total in my data set. Now I am say going to create 3 models. Alright. Now in my model 1, say I have chosen only sepal length and sepal width. Model 2 I have chosen randomly. Say I have chosen sepal width and petal width. Sepal width, petal width. Alright, and my target is of course going to be their species. This is my target. And say in model 3 I have chosen sepal length and petal length. Alright, in my model 1 say I have chosen 1, 4 and 5 rows. In my model this 2, for my model 2 I have say chosen 2, 5 and 6. In for my model 3, this small data set 3, I have say chosen 3, 5 and 6. Alright, so this is what I'm going to do. The point to notice here is this. In my data, small data set 1, I have chosen row 5. In small data set 2, I am choosing row 5 again. Alright. In small data set 3 also I am choosing row 5. This may happen. I am choosing randomly of course. So just because I have chosen uh, 5 in small data set 1 does not mean my probability of choosing 5 in small data set 2 is going to decrease. Or if I choose small data set in small data set 1 and 2 I have chosen row 5 does not mean the probability that I choose small row 5 in small data set 3 is going to decrease. Alright, now let us look at column as well. I have chosen sepal length and sepal width. Now sepal width I have chosen here. Sepal width I can choose this column here again in my small data set 2. Alright, I have chosen in small data set 1, I can choose in small data set 2 as well. Alright, so this fact that I can choose the same row to be part of two different data set or the same column to be part of two different data set, this is called bootstrap sampling. Alright, so we are going to choose with replacement. That means once I have chosen, I may choose that again in a different data set. Now in the same data set, I am not going to choose the same row two times. So don't confuse that. Yeah. So this is a code to do bagging using scikit-learn. Now let us go ahead and talk about this very popular technique for bagging. It is random forest. So in random forest, we are going to create decision tree, right? So we are going to create small data set 1, small data set 2, and we have created small data set n. All right. So from this different small data sets that we have created, this data set is say going to give me this tree. This second data set is going to give me this second tree. Third data set is giving me, this n data set is giving me this n3. So from this n different small data sets that we have created, we are going to apply some decision tree algorithm. Say ID3 we have learned, or there is another algorithm called CART. So CART is the algorithm that is used by default in sklearn. Say we are going to use CART. So using this CART algorithm on this n different trees, we are going to create n different using this CART algorithm on this n different data set, we are going to create n different trees. Alright, so I am going to take this CART algorithm, apply it on decision tree, this small data set 1, and I am going to get my tree 1. Then I am going to take this CART algorithm, apply it on small data set 2, I am going to get my tree 2. Alright, in this way I have got n different trees. So each tree in the ensemble is built from a sample drawn with replacement. So how do we build? We create each tree on this small data set, alright, that we have built on a sample drawn from the original data set with replacement. That is, we have done bootstrap sampling, alright, from the training set. That is what we have to do. Each tree in the ensemble is built from a sample drawn with replacement, that is bootstrap sample from the training set. Alright, now not only are we going to choose the sample randomly, but we are going to choose the features also randomly. Alright, in addition, instead of all the features, a random subset of features is selected. So this further randomizes the tree. So not only are we choosing our rows randomly, we are choosing our columns randomly as well when we create random forest. Alright. Now, because of this, the bias of the tree might increase slightly. So, on our training data, we may have more error. Our random forest may give more error than we would get using a single decision tree. Now, why is this? This is because a single decision tree can fit our training data very properly. Given all the rows, given all the features, decision tree have this tendency to overfit data. So on our training data, when we create a decision tree, we are going to get very good accuracy. All right, but our accuracy on test data, because decision tree can overfit, therefore on test data our accuracy is not going to be that good if we use a single decision tree. Now with random forest, what will happen is, unlike in a decision tree where we get very good result in training data, random forest may not perform as good in our training data, right? So that is what it says. The bias of the forest increases slightly, all right, but because we have many trees, all of them are doing different output, all right. Most of the trees, if they are correct, then uh, most of my testing data, on my testing data, we are going to have better performance than a single decision tree. So variance is going to decrease. So because variance decreases, we are overall going to have a better model. Now, given some unknown data, how are we going to go ahead and classify? Now, given this unknown data, uh, all right, we are going to feed the unknown data to all these trees that we have created. all right, and say this is a yes no classification. Say my tree 1 is saying no, my tree 2 is saying yes, my tree number 3 is saying n is saying yes. So in this way, say 60% of my trees are giving the output yes, 40% of the trees are giving the output no. In this case, what is happening? This class yes is winning the vote. So there is was some voting. Class yes has won the vote, and therefore the final output that my random forest is going to give is yes. Alright. So this is what we have. This is random forest. Now let us go ahead and look at a code, scikit-learn code to do random forest. Very easy. Here we have loaded the iris dataset. X contain all the features, Y contain the target, and here is where we have created a random forest classifier. So random forest classifier we have created with 100 different trees. So we are randomly going to choose rows and we are going to randomly choose column. So we are not going to each of this tree, all right, we are going to create 100 different tree. Each of the tree is not going to contain all the rows, and none of the tree are going to contain all the columns. We are randomly going to choose row and we are randomly going to choose column, and that is how we are going to make 100 different tree. And once we have this 100 different trees, we are going to train 100 different models on this 100 sorry, once we have this 100 different data set, small data set, we are going to create 100 different trees on this 100 different small data set. And then what we are doing here is we are doing five-fold cross validation using these trees that we have created. All right, and then we print the average score. All right, so this is what we have. This is uh, essentially one line of code again to create a random forest classifier using scikit-learn. Then another line of code to do k-fold cross validation on this dataset that we have created. All right, so you can see how good scikit-learn is using two lines of code. All right, these two lines are essentially to load the library. This three lines essentially to load library and dataset. This one line to load the dataset into x and y features and column, and then this two line to do random forest to create random forest classifier, and then to do k-fold cross validation using this random forest classifier. Essentially, using only two line of code, we can do very complicated things using scikit-learn. So it's a very good library that you should be very familiar with. Alright, so this is random forest. Now up to this point we did not talk about any algorithm, we did not go into depth of any algorithm. Alright, so the algorithm that we are going to use, we already discussed that in our previous two videos. So not going to look at algorithm in this video, just talking at a very high level of how this meta algorithm are going to work. All right, and that itself should give you very good idea of how to implement these things, how these things work behind the scene. All right, there is nothing very technical, nothing very deep that we are doing up to this point in bagging and in random forest. All right, so we are going to use these simple things that we have studied in our previous videos, and yeah, that is how we are going to do the classification. All right, now let us go ahead and look at the next technique. So the first technique that we talked about was bagging. We learned a very popular technique in bagging. It is okay, there is a dog barking, sorry about that. This dog has a habit of barking a bit too much. All right, so so there is this dog in my neighborhood, sorry about that. Anyway, uh, so the first technique that we saw is bagging, and random forest is a very popular technique in bagging. Now the next technique that we are going to look at is boosting. Now, boosting refers to a family of algorithms that are able to convert weak learners to strong learners. Now, we are looking at two different words. Alright, weak learner and strong learner. I will soon talk about what this means. Uh, or let's talk about what this means. Strong learner, for example, is what we use in decision tree or in random forest. Alright, these are full-fledged decision tree. For example, if I have to create a tree that has a depth of that has a height of say 5, then I will go ahead and create a tree with a height of 5. Alright, so these are full-fledged complex models, strong learners. Now contrast that to weak learner. In weak learner, if I use a tree, these are going to be very shallow tree. Alright, say this, I am looking at sepal width greater than equal to 4.5. Okay, this is a test that I make, and then based on this test, I am going to split my data set into two. In strong learner, I will have a data set over here, I will have a data set over here, and I am going to make say another test here. Okay, so in this way I may make more tests and I may grow. I make more tests over here, I grow, then I have a leaf. So I have leaf over here. This is an example of a strong learner. Okay, or this may happen. I may have more test over here. Okay, and then I have a leaf here and a more test here and then leaf over here. So my tree is going very deep as necessary. Now, in a weak learner, what is going to happen is I am not going to have such a complicated model. Okay, I do a test here, and based on the output of the test, I am going to have leaves directly over here. Okay, my data set is going to be split, and we are going to look at the how we split it, and we are going to have leaves directly uh, next to the root. So I have one root of the tree, one internal node, that is my root node, and just below the root node I am going to have leaves. So there are not going to be any other internal node in my tree. Alright, now in a strong learner I will have many internal nodes. I will have a root node and I may have other internal node as well. But in a weak learner, I am going to have only one root, that is going to be my only one internal node. My root itself is going to be my internal node, and after my root I am going to have leaves directly. So this is an example of a weak learner. Now one more terminology. This kind of trees, alright, where I have one root node, my only internal node, this root node, and just below root node I am going to have leaves. So if I have this kind of a tree, these are called stumps. Alright, so a bit of terminology. Henceforth, if you hear me saying the word stump, then understand that I am talking about weak learner. What kind of weak learner? A decision tree. What kind of a decision tree? A decision tree where I have one node, one root node, and below the root node I am going to have uh, this directly. I am going to have leaves directly. Alright? Okay. So boosting uses weak learner, and it is going to use lots of weak learner, and together they are going to come together, and that is how I am going to have some complicated learning algorithm that is strong. Alright. So I am going to create this strong learner which is my boosted ensemble, and that ensemble itself is going to be created with lots of weak learners. Now the main principle of boosting is to fit a sequence of weak learners. Now once again, another way of looking at weak learner, these weak learners, they are not this good, right? A complicated decision tree with many levels, with a height of greater than 1. Okay, a full-fledged decision tree will be giving me very good output, all right, but will be able to do very good prediction. But this kind of weak learner, this kind of stumps, this tree that you see on your screen right now, this shallow tree, is not going to be as good as a full-fledged decision tree. All right. So this kind of a tree is not going to give very good accuracy. All right. Not going to have a very good performance. This kind of a tree are going to be only slightly better than random guessing. Okay. Not as bad as random guessing, but only slightly better than random guessing. All right. So this is what we are going to have. We are going to feed a sequence of weak learner. So what does that mean? I am going to create my first weak learner. Based on the first week learner, I am going to create the second week learner. Based on the performance of the second week learner, I am going to go ahead and create the third week learner, and so on. Alright, so we are going to do sequential ensemble. Now, the main principle of boosting is to fit a sequence of weak learner. What is weak learner? Model data on is slightly better than random guessing, such as small decision tree, two weighted version of the data. So data is going to have some weights, and we are going to train this tree on the basis of those weights. All right. So more weight is given to examples that were misclassified in the earlier round. We will talk about what this sentence means very soon. Now, how is the prediction going to be done? Now, prediction is going to be done on weighted majority vote. All right. So, say this has some weight. This has, say, this stump, this weak learner, this shallow decision tree that I have created, the first one, is able to do classification a bit properly. Okay. So, this is, say, good. All right. Now, this say does not do classification very properly. This is a bad, and this does classification slightly better than bad, but not as good as good. So this is the average. All right. Now, when I have to make the final classification, when I uh, combine the output of all these terms, so when I have a unknown data, I will make all these terms try to classify this unknown data. All right. So I will do just one test. Each stump is going to do just one test, and based on the output of this test, each stump is going to give me a class. All right, so I'm going to reach this libs directly, and each stump is going to give me a class. Now this stump is giving me some output, this first. Second stump is going to give me some output. Third stump is going to give me some output, and that is how I am going to have all these multiple stumps are going to give me multiple output. All right. Now, unlike before, unlike bagging, in bagging, I just did a normal voting like we do in election. Everyone's vote has equal weightage. Here, this term that has a good performance is going to have a higher weight. The vote of this term is going to have a higher weight compared to the vote of this term, the bad stump. The bad stump is going to have the lowest weight. Now the average stump vote is also going to count. It will come between the good stump and the bad stump. So there is going to be some sort of a weighted voting. Alright. So weighted majority vote is something that we are going to do if we are doing classification, or there is going to be some weighted sum, weighted average that we are going to do in case of regression. Alright, and that is how the final prediction, the final output of my ensemble method is going to be calculated. Alright, now a bit more about boosting. When does boosting work best? Boosting work best when we have weak learners. So boosting method works usually work best with weak models, that is a shallow decision tree. So shallow decision tree, we are going to be really shallow. In fact, our decision tree that we are going to create, the weak learners that we are going to create are so shallow that I have only one internal node and then below that internal node I am going to have leaves directly. Alright, so if I have this kind of weak learner, then boosting is the way to go. Contrast that with bagging. When does bagging work best? Bagging work best with strong and complex models. So fully developed decision tree, say big decision tree, if we have those kind of things, like we did in random forest, so in that case bagging is the way to go. All right, but if we have weak learners, then we should go with boosting. Now one technique to do boosting is AdaBoost. Now let us go ahead and talk about AdaBoost. Alright, the core principle of AdaBoost is to fit a sequence of weak learner. So once again, what are weak learner? Models that are only slightly better than random guessing, such as small decision tree. Alright, so we are going to fit a sequence of weak learner. So I am going to create my weak learner 1. Based on the performance of weak learner 1, I am going to create my weak learner 2, and so on. Alright, on repeatedly modified version of the data. So how are we going to create weak learner 1? I am going to create on my original data set. Alright, and based on how the weak learner 1 performs on this original data set, I am going to create my second data set. And second data set is going to be modified in such a way that the errors that I make in my using my first weak learner, uh, we will try more to uh, remove those errors using the second weak learner. Alright, so my second weak learner is going to focus on trying to remove the errors that my first weak learner makes. Alright, so this data set that I generate is going to be modified so that my the errors that my first weak learner makes on this data set are given more priority in this data set. Alright, so that is what we mean by repeatedly modified version of the data. Then how is the prediction done? The prediction from all of them are weighted. There is a weighted majority vote. So this is going to have some performance. This is going to have some performance. All my weak learners are going to have different performance. The performance that my the weak learners that have better performance, the vote of those weak learners are going to have more weight compared to the weak learners that have worse performance. All right. So in this way, we are going to have weighted vote, and that is how we are going to produce our final output. So already talked about the basic idea behind this when we talked about boosting in the last slide. Alright, so this is AdaBoost. Now let us go ahead and uh, see how AdaBoost works with a dataset. This is the dataset that we are going to be looking at. Now, one thing that I want to tell you in advance, if you did not see the last two videos, then this is the time to pause this video, go back and watch those two videos, and then come back and watch this video from this point onwards. The dataset that you see on your screen right now is the dataset that we looked at in our last video. Alright, so this is the dataset that contains the patient detained for 8 different people. These are the 8 different people over here. Alright, this row, for example, means that there is a patient who had chest pain, who did not have blocked arteries, and the weight of the patient was 210 pounds, and the patient had heart disease. This row in my dataset, for example, means that there is a patient who had chest pain, who had blocked arteries, and the patient's weight was 172 pounds, and the patient did not have heart disease. So this is what the dataset means, and there are data for 8 different people. You can see there are 3 features and 1 target. Now the next thing that I am going to do is I am going to assign weight to each of these rows. So let us go ahead and do that. Now how much weight do I assign to each of these rows? Okay, initially all these rows are going to have the same weight. Now there is this one criteria when I'm going to assign weight. The sum of all this weight should be equal to 1 or should be almost equal to 1. Okay. There are going to be times when we cannot have 1, but should be almost equal to 1. Alright. Now how do I assign this? There are 8 rows. Now I am going to assign a weight of 1 by 8, 1 by 8 to each of them. 1 by 8 is equal to 0.125. So I am assigning weight of 0.125 to each row. Alright, and this is what I have, 1 by 8 which is equal to 0.125, and 0.125 into 8 is equal to 1. So the sum of all this weight is going to be equal to 1. Alright, so this is what I do. I have assigned weight of 0.125 to each of the row. Let us not talk about weight anymore. Okay, we will come back and talk about weight when this weight column is going to be relevant again. Okay, now I am going to create stumps. How do I create stump? Now, what do I mean by that? I have this data set. I am going to create a stump like this. There is going to be some sort of a test over here, and based on the test I am going to split my data set. For example, here I have split it on chest pain. If chest pain is equal to yes, I go in this branch. These are the 5 rows where chest pain is equal to yes. Alright, and if chest pain is equal to no, I go in this branch. These are the 3 rows in which chest pain is equal to no. Alright, in that way I have split it on chest pain. I could have split it on block artery. If I split on block artery, this is the branch where block artery is equal to yes. These are the rows in which block artery is equal to no. So all the rows with block artery equal to yes. This and this. This rows comes over here. All the rows with block artery equal to no. This and this goes over here. Alright. These are the rows with block artery equal to no. So I could have split it on chest pain. I could have split it on blocked artery. Now, what do I split on? Do I split on chest pain or do I split on blocked artery? Or I can split on patient weight. We will talk about that as well. But right now, let us look at chest pain and blocked artery. Okay. Which one do I choose among these two? We will soon talk about patient weight. But among these two, what might I choose? How do I decide that? I can either look at information gain or I can look at Gini index, Gini impurity. Alright. If I look at information gain, then out of these two, whoever has the higher information gain, I will be choosing that. If I look at Gini impurity, out of these two, whoever is having the lower Gini impurity, I am going to choose that. Alright. So what do I choose? Gini impurity or information gain? That depends on you, does not really matter. I'm going to do Gini impurity. Why? Because Gini impurity is faster to compute. Alright, so let us go ahead and compute the Gini impurity. The Gini impurity of this data set is going to be 0.48. The Gini impurity of this is equal to 0.44. Therefore, the total Gini when I split on chest pain is equal to 0.47. Alright. The Gini impurity of this is equal to 0.5. The Gini impurity of this is equal to 0.5. And therefore, the total Gini that I get after choosing splitting on blocked artery is equal to 0.5. Now, if these are not making sense to you, how we are computing all of these things, that means you have not watched the last 2 videos. So go back and watch the last 2 videos before watching this video. Alright. So this is how we get the Gini When I split on chest pain, this is the Guinea that I split on blocked artery. In the last two videos, we have explained everything: how to compute Guinea, what is information gain, how to compute information gain. So there is no point watching this video without watching the last two videos. Alright, now, yeah, do I split on chest pain or do I split on blocked artery? So definitely I am not going to split on blocked artery, right? Why? Because this has a higher Guinea impurity, this has a lower Guinea impurity. So I might split on chest pain, I don't know that yet, but I know this, that I am not going to split on blocked artery. So this is out of question. Alright, now I might split on chest pain, I don't know. Let us go ahead and look at splitting on patient weight. Now before we talk about splitting on patient weight, one observation that we have to make is that patient weight is continuous, unlike chest pain and blocked artery. Chest pain, it was very easy, this was discrete. So if chest pain is equal to yes, we could have taken this branch. If chest pain is equal to no, we would have taken this branch. But uh, patient weight is continuous. So how do we handle patient weight? We are going to have a threshold. Alright, so 176 is the threshold that we have chosen. Why did we choose 176? Because out of all the possible threshold using which we could have splitted this patient weight, 176 gives us the best Guinea impurity. Alright, therefore we have decided to split on 176. Now if we split on 176, we are once again going to split our data set into two parts. This is the part where patient weight, the result of this is this test. Is patient weight greater than 176? This is the test that we are going to do. If patient weight is greater than 176, is patient weight greater than 176? If my answer is yes, I am going to take this branch. So this data set contains all the rows. Alright, this and this, where patient weight is greater than 176. Is patient weight greater than 176? If my answer is no, I am going to take this branch. So this contains all the patient weight where all the rows where patient weight is less than 176. So this is how I am going to split. Why did I choose 176? Go back and watch the last video. Alright, now if I do this split, then this data set is going to have a Guinea impurity of 0 because this is pure. Alright, and this data set is going to have a Guinea impurity of 0.32. Alright, that means there are some impurity. 4 of these classes are no, 1 is yes. So there is some impurity. Alright, so the total Guinea that I get on splitting this data set using this test, that is patient weight, is patient weight greater than 176? That is the test that I am going to do. Alright, so if I split on this test, the Guinea impurity that I get is 0.2. The Guinea impurity that I get on splitting on chest pain is 0.47. So which one do I choose? Do I choose to split on chest pain or do I choose to split on patient weight? Patient weight is going to give me the lower Guinea impurity. I am going to choose the split that gives me the lower Guinea impurity. Therefore, I am going to choose to split on patient weight. I am not going to go ahead and split on chest pain. Alright, so I have decided to split on patient weight. Fine. That is what I am choosing. Alright, now what do I do? In our last video, we saw this as a Guinea of 0. Therefore, we created a leaf node over here with class level yes. So all the classes in this data set are yes. Alright, we know that this class is pure. How did we know that? Because our Guinea was 0. Alright, because our Guinea impurity is 0 and all the classes in this data set has the class level yes. Therefore, we could have we created a leaf node over here with the class level yes. That is what we did. And what else? What did we do with this data set? We splitted it further, right? We had to work with patient weight, so we had these two features left: column chest pain and blocked artery, and we worked further with these two columns. So that is what we did in our last video. But here we are creating weak learners. In fact, so weak that we are creating stumps. That is, we are going to have one root node, one test. This is the test that we are going to have, and then below that we are going to have leaf node directly. There is not going to be any more split. In the last video we split it further, but we are not going to do that anymore. Alright, so I have to create a leaf node over here. So if I create a leaf node with this, what is the class that I should write over here? So I see that out of these 5 rows, 4 of them are no and 1 is yes. Therefore, majority of the uh, classes here is no. All right. So therefore, I am going to create no as the leaf here. This leaf is going to have the class label no. All right. So this is what I do. This is how I create my first stump. Let us go ahead and do that. This is the stump that we have created. Alright, our first stump. Alright, fine. Now we have to talk about how much error are we making on our training data using this stump. So if patient weight is patient weight greater than 176, that is the test that we make. If my answer to that test is yes, yes, patient weight is greater than 176, I am going to take this branch. If my answer is no, I am going to take this branch. Alright, so that is what we had. Here also this is yes, this is no. Yeah, this is the sum that we have created. Let us see how good is my stump performing. Okay, let us look at the first row of the data set. Patient weight is greater than patient weight is 205. Is patient weight greater than 176? Is 205 greater than 176? Yes. Therefore, I am going to predict yes. Is my prediction correct? Yes, my target is yes. I had predicted yes, my target is yes. Therefore, my prediction is correct. Then the next row, patient weight is 180. Is 180 greater than 176? Yes. Therefore, once again, I am going to predict yes. My target is also yes. Therefore, again, my classification is correct. Next, I am going to look at the patient weight 210. Is 210 greater than 176? Yes. 210 is greater than 176. Once again, my stump is going to predict yes. Alright, let us look at the data set. Data set target is yes. Therefore, once again, I am correct. This is also correct. Let us look at the third row. 167. 167. Is 167 greater than 176? No. Therefore, I am going to take this branch and I am going to predict no. Let us go ahead and look at the data set. Data set says yes. Okay, the target in my data set is yes. I had predicted no. Am I correct? No, I am not correct. Alright, so I made a error. Using this stump, when trying to classify my training data, this is an error that I made. Let us go ahead and work with the rest of the rows. 156, is 156 greater than 176? No. Therefore, I predict no. I am correct in my prediction. 125, I predict no. Answer is no. Target is no. Therefore, I am correct again. 168, I predict no. Okay. Target is no. I am correct again. 172, is 172 greater than 176? No, it is not. Therefore, I take this branch like I did in the last 3 rows. And I am going to predict no. Okay, I have predicted no. Is my prediction correct? I go and look at the dataset. Dataset says that the target is no. I had predicted no, target is no. Therefore, I am correct. Okay. So out of all these rows, out of all these 8 rows, one of them is incorrect. I made a mistake in one of them. Alright. So what is my total error? My total error is going to be 0.125. Alright, so the total error that I make is the weight of all the errors, is the sum of weight of all the errors. Alright, so here I made only one error, therefore the total error is 0.125. Now that I have calculated the total error, sorry, okay, now that I have calculated the total error, I have to calculate how good is this stump. Okay, so in my final classification, how much weight this stump is going to have. So that is what I am going to calculate next. I am going to calculate in my final classification how much say this stump is going to have. Alright. So in my villages, for example, the leader of the panchayat has lots of say in village matter, and then some random person, he does not have that much say in village matter. In the same way, I have to calculate how much say in my final prediction this stump that I just created using this split. Patient weight, is it greater than 176? If yes, then I go ahead and classify yes. If no, then I go ahead and give no as my classification output. This is the stump that I had created. This was the stump that gave me the best Guinea impurity, that gave me the lowest Guinea impurity. Lowest is the best on my training data set. So this is the stump that I had. All right. Now, how much say does this stump going to have in my final prediction? This is the formula. Okay, this is log base e, the natural log. In your calculator you will see ln. Okay, so this is the formula. Okay, now how does this formula work? If I make before we talk about how much this formula work, what is the range that total error may have? If I do not make any error at all, okay, in that case I am going to have a error of 0. And if I make error in every line, then what is going to be my total error? So we already talked about this when we were assigning weight. We talked about this criteria that the sum of all the weight has to be equal to 1. All right, so if I make a error in all the rows, then I am going to have a error of 1. All right, now if I have an error of 1, I am going to have a very high value. If I give a error of 0, I am going to have a very low value. That means, sorry, if I have a error of 1, I am going to have a very high negative value. If I make a error of 0, I am going to have a very high positive value. Okay, so if I am all correct, I am going to, my amount of say is going to be very high. This tree is going to have a very high weight in my final classification. All right, and if I, my total error is very low, if I make lots of mistakes in doing classification, I am going to have a very high negative value. My amount of say is going to be very small, a large negative number. All right, and the say that I have this, that this tree, that this stump is going to have, is going to be very low in the final classification. Now, what if this stump is making random guess? All right, it is neither making good prediction nor making bad prediction. So it is making random guess. It is flipping a coin. Okay, in that case, I'm going to be correct 50% of the time and wrong 50% of the time. If that happens, if my error is 0.5, okay, I am wrong half the time, then this tree is going to have a say of 0. Alright, if I make, if then this tree is not going to influence much. Alright, if I make lots of error, then the tree will not be uh, is going to be ignored a large part. All right, the prediction of the tree will have negative weight. If I make no error, then the tree is going to have positive weight. All right, so it is going to matter a lot. If I do 50-50, it is neither going to matter nor is it going to be ignored. It will simply stay. Alright, so this is what it is. Now, one more thing that you should observe is this. If I am all correct, then my total error is going to be 0. If I have 0, alright, so this formula is going to be half natural log 1 minus 0 divided by 0. Alright, this is going to give me a uh, divide by 0 error. Alright, when I try to calculate. On the other hand, if I make all mistakes, alright, then I am going to have a total error of 1. So 1 minus 1 by 1, and this is going to be natural log of 0. Alright, this is also undefined. Like divide by 0 is undefined, in the same way finding log of 0 is also undefined. So if I'm making all correct, all mistakes, then I'm going to have some uh, programming error, I'm going to have mathematical error. Alright, therefore what we should do is we should add a very small number to both the denominator and numerator. Alright, a very small number, a fractional number to the numerator and denominator, so that we do not end up with this divide by 0 or uh, log of 0 is undefined, those kind of error. Alright, this is just for programming convenience, or this is just for mathematical convenience. Right, so that is one observation that we have made, and this is the formula to find amount of say. All right, how much weight, how much say this stump that we have created is going to have in our final classification. How much weight does this stump have? All right, so we have created a stump right now. We saw that the total error was 0.125. Alright, we made a mistake in only one row. That row had a uh, weight of 1 to 5. So my total error is the sum of weight of all the rows in which I made mistake. Therefore, that stump had a error of total error of 0.125. Let us go ahead and calculate what is the amount of say that the stump is going to make. Alright, so this is half log base e natural log 1 minus 0.125 divided by 0.125. This is in fact half log e base 7. Alright, and this is 0.97. Okay, so this is the amount of say that this tree is going to have. Okay, now let us look at what would have happened hypothetically. This is not something that we are going to do. We are going to split on patient weight equal to patient weight with a threshold of 176. So this is the test that we are going to do is patient weight greater than 176. So that is the test that we are going to do. But hypothetically speaking, what if we had split it on chest pain? Alright, if we had split it on chest pain, if this is the test that we had chosen, if this is the stump that we had chosen as our first stump, then this is the split that we would have done. Alright, and here I have all the rows with patient is with chest pain equal to yes. Here I have all the rows with chest pain equal to no. Alright, so I see most of the classes here is yes. Therefore, this will become a leaf node with yes class. I see most of the classes here is no. Therefore, this will become a leaf node with no class. So, if I would have split it on chest pain, this is the stump that I would have gotten. Alright. So, let us go ahead and see what would have happened had we chosen this stump instead of the stump that we had chosen. This is not the stump. Once again, we are not going to use this. This is just a hypothetical situation. Alright. So, had we chosen this, then okay, this is yes branch, this is no branch. Let us go ahead and predict for each of the rows. So I'm going to go ahead and predict for this row. Is chest pain equal to yes? Chest pain is yes, so I would have predicted yes. My answer is yes, so I would be correct in this row. Chest pain, this says no, but I would have predicted yes, but my target is sorry. Chest pain is no. I would have predicted no, but my target is yes. Therefore, I will be incorrect here. Here, chest pain is yes. I would have predicted yes. My target is yes. Therefore, I would be correct here. Here, chest pain is yes. I would have predicted yes. My target is yes. I would be correct here. Here, chest pain is no. I would have predicted no. My target is no. Correct here. Chest pain is no. Uh, Chest pain being no, I would have taken this branch. I would have predicted no. My target is no. Once again, I am correct. Here, chest pain is yes. Alright, I would have taken this branch. I would have predicted yes. My target is no. I would be incorrect. Again, chest pain is yes. I would have taken this branch. I would have predicted yes. My target is no. Therefore, I will be incorrect. Okay. Now, what is the total error? My total error, I have made an error in this row, I have made an error in this row and this row. Therefore, my total error is 0.125 plus 0.125 plus 0.125. Alright, the sum of the weight of all the rows where I have made mistakes. Alright, so this is equal to 0.375. Alright, therefore, what is the amount of say that this tree would have had? This stump would have had a error of half log e base 1 minus 0.375 divided by 0.375, and that would be equal to 0.2554. So had I used this stump to do the classification, this is the amount of say that the stump would have had. But we have used the stump where we are using 176 as the threshold on patient weight. Alright, and that had a amount of say of 0.97. So that was good. So that had a higher amount of say. This is bad. Okay, that stump made an error in only one row. This stump is making an error in 3 rows. Alright, therefore it makes sense that this has a smaller amount of say. This would have had a smaller amount of say than the stump that we had chosen. Alright, now we are done. Okay, we had chosen our first stump. Before we go ahead and create our second stump, now we have to work with the weights. So this is the weight that we had originally. Our original weight was 0.125. Now we have to update the weight. Okay, we update our weight using the following rule. For the rows which were incorrectly classified, for the rows that were incorrectly classified, the new weight is equal to the old weight into e to the power amount of say. Okay. Now what does this do? If my stump is making random guessing, my new weight is going to stay the same. I am going to multiply by 1. This is the scaling factor. By how much do I change my old weight? Alright, my new weight is my old weight into something. This something is going to either increase if this something with which I multiply my old weight is greater than 1, then this old my new weight is going to be greater than my old weight. If that something is less than 1, then my new weight is going to be less than my old weight. Alright, so what is this thing? If I am doing random guessing, I am multiplying by 1. Therefore, my new weight is going to be same as my old weight. If my tree is good, if my amount of say is good, alright, bigger than 0, then the more good, the better my tree is, better my stump is, the larger is the scaling factor. Okay, so the incorrectly classified weight, the rows that were incorrectly classified, the weight of that is going to improve, is going to increase a lot. If my tree is good, a tree that makes good classification, all right, and a sum that makes good classification, the rows in which it was incorrect, those rows are going to improve their increase their weight by a large amount. All right, so that is what we are going to do, and figure out what happens if my stump is bad, is worse than random guessing. Okay, then we are going to multiply by some number smaller than 0 and my weight is going to shrink. All right, it's going to become small, but let us not worry about what will happen if my stump is worse than random guessing. All right, uh, our stump is definitely better than random guessing. It has a positive amount of say, therefore I am going to multiply by some number greater than 1. This is 1, and we are going to multiply some number with some number greater than 1. Alright, so this is what we do with the rows that were incorrectly classified. Alright, the rows that were incorrectly classified, those rows weight are going to increase. What about the rows that were correctly classified? Once again, the same kind of formula with one minor difference. There is a negative sign in front of amount of say. All right. In case of this incorrectly classified, this negative sign was not there. All right. So the graph shifts. If I am doing random guessing, once again I am not going to make any change. I am going to multiply by 1. The old weight is going to be multiplied by 1. All right. But if my say is better, then what is going to happen? This correctly classified rows, I am going to multiply with a number less than 1. Alright. So, what is going to happen to this correctly classified rows? The weight of those rows is going to decrease. Alright. So, what we are doing here, if my stump is good, that is I have a positive amount of say, then uh, the incorrectly classified rows, the weight of those are going to increase, and the correctly classified rows, the weight of those are going to decrease. All right, and if my tree is bad, then what is going to happen is this. uh, if my tree is bad, then incorrectly classified rows weight is going to decrease, and correctly classified rows those weight are going to increase. All right, but my tree is good, I have an amount of say greater than 0.97. All right, so we are always going to choose these stumps which give us better than random guessing, right? If all the stumps that are possible, none of them are better than random guessing, then this technique, AdaBoost technique, is not the way to go forward. So we will always choose stumps that are better than random guessing. So definitely better to concentrate on this side of the graph. So this is what it is. All right. Uh, Once we have created a stump, once we have chosen how to split this stump using Gini impurity, then we calculate how much say this stump is going to have in the final classification. Once we have done all these things, now it's time to update our weight. Alright. So when we update weight, these are the formulas. And what does this formula do? The incorrectly, whatever rows we classified incorrectly using the stump that we have generated, the weight of those rows are going to be increased. Whatever rows we classified correctly, the weight of those are going to be decreased. So that is what we do. Let us go ahead and calculate what would be the new stump. This and this were correct. This was incorrectly classified. This and this were correctly classified. So 7 of them were correctly classified. So new weight for correctly classified is going to be old weight 0.125 into e to the power minus amount of say. The amount of say of this stump was 0.97. Therefore, e to the power minus 0.97, and this is equal to hold on, 0.0474. Let me round this up to 0.05. All right, and new weight for the incorrect is going to be 0.125 into e to the power 0.97, and that is equal to 0.3297, and I'm going to round this up into 0.33. Alright, so the new weight of this is going to be, first row is going to be 0.05, second row is 0.05, third row is 0.05, fourth row is 0.33, fifth row 0.05, 0.05, and so on. Alright, so this is what we have. This row was incorrectly classified. The weight of this row increases. All this row were correctly classified. This is 0.05, alright, not 0.5. All this weight they decrease. Alright, the rows that were correctly classified, the weight of those decrease. Alright, let us go ahead and talk about this a bit more. These are the new weights that we have calculated. Now if I see, if I add them up, I am going to see the sum is equal to 0.68. Alright, now what was the criteria that we talked about? Our sum has to be equal to 1. The sum of the weight have to be equal to 1. Alright, but here we see that the sum is equal to 0.68. So what do I do? I have to make sum equal to 1. I'm going to normalize them. Okay. What I'm going to do is I'm going to divide each of them by 0.68. So let us go ahead and do that. Okay. This I'm going to, the sum is 0.68. Therefore, this is going to be 0.05 divided by 0.68, and that is equal to 0.0735. Alright, then this is also 0.5 divided by 0.68, 0.0735. This is also 0.0735. Alright, this is 0.33 divided by 0.68. This is going to be hold on, 0.4852. Alright, this is 0.05 divided by 0.68, 0.0735, 0.0735 again, and finally 0.0735. Alright, so this is what we have. These are the normalized weight that we have calculated. Alright, now if I add them up, I am going to see this is equal to 0.9997. Alright, now yeah, this is a thing that is going to happen. If I had taken more significant digits after here, okay, this would be even more precise, 99997 say. Alright, but I may not get 1. Alright, this is because of rounding error. Uh, my PC, my calculator, all of them are going to have fixed size register. Alright, or I'm going to have some limit on how many significant digit I'm going to calculate. So based on that, I'm going to have some rounding error. Alright, so I may not have 1, but 0.9997, I got the sum equal to 9997, and I'm going to accept that. Alright, so yeah, let's go ahead and think about what to do. These are my updated weight. Alright, and what I'm going to do is I'm going to make a number line that goes from 0 to 1. Okay, now this 0.0735 At a distance of 0.0735, I am going to have this, and this has a distance of 0.0735. This has a distance of 0.0735. Similarly, this has a distance of 0.0735. This has a distance of 0.4852. All right, and again these all have distances of 0.0735. All right, all of them. So this is how I have splitted my number line. Okay, and now I am going to create my uh, data set for the next row. All right, now how am I going to create the data set for the next iteration? So how am I going to create that? I'm going to use this number line. All right, now in my next data set, in my new data set that I'm going to create, my focus is what? My first tree has done what? It has accurately classified all these rows. All right, so the next data set that I create, my focus will be on classifying the row where I made a mistake. All right, and the row where I made a mistake has a higher weight, therefore it has a higher, it takes up a higher proportion of this number line. Since I have split it based on these weights that they have, therefore uh, most of my area in my number line is taken up by the rows. Here I have only one row, but majority of the area is going to be taken up by the row that makes mistake. Okay, this for example is a row that was correctly classified. It takes a small area compared to this that made a mistake. This takes up a large area because those that were correctly classified has a small weight, and those that were incorrectly classified, where I had mistakes, has higher weight. So this is what is happening. All right, now how do I generate the next data set? Okay, this is going to be interesting. Okay, I'm going to generate the next data set, and what I'm going to do is I am going to generate random numbers between 0 and 1. Okay, now it so happens that this region has a distance of 0.4852. All right, therefore almost 50, therefore 50% of the time I'm going to generate random numbers that fall in this region. All right, and that is something that will be my focus. Okay, let us go ahead and generate random numbers. The first random number, say I generate, is 0.72. Okay, so 0.72 falls in this region. All right, therefore I am going to choose row number 5. So I come here, I choose row number 5. Row number 5 says no, yes, 156, heart disease is no. Alright, so this is how I have chosen my first row. Then I generate random number again, 0.42 say. 0.42 comes here. So I am going to choose the fourth row. Alright, this corresponds to fourth row. That is what I am going to choose. So this is yes, yes, 167, yes. Alright, then I generate another random number, 0.83. 0.83 comes over here, so I'm going to choose row number 7. Alright, this says yes, no, 168, and no. Then I generate another random number, 0.51. So 0.51 corresponds to uh, this region. Okay, this corresponds to row number 4. So again I am going to put row number 4. Yes, yes, 167, yes. Alright, and I keep doing this. I keep generating random number and I keep choosing here. I keep choosing, I see, I generate a random number I see where does the random number fall, what is the row that it corresponds to. I choose that row and I put that over here. This is how many rows am I going to choose? I had originally 8 rows in my training data. So this is how I am going to choose 8 rows in total. So let us go ahead and do that. This is how I have chosen this 8 rows. Alright. Interesting thing to observe. This one, this and this. I had chosen row number 4. Alright. Which had a higher weight. That was incorrectly classified. I am choosing that 4 times in this new data set. Alright. Now I have to assign weight again. Once again, if I have n rows, I am going to assign 1 out of 8 n to each of the row. I have 8 rows, therefore I am assigning 1 of 8. This is equal to 0.125 to each of the row. Alright. Once again from the very beginning. Now I am going to create a stump that base separates this data set. Alright. Uh, whether on chest pain, whether on blocked artery, or whether on patient pain. I'm going to create a stump that does the best classification again, like I did in my first data set. So I'm going to repeat this process. Alright, at the end of this process, I would have created a stump and I would have created another data set. And then I repeat again, I would have created another stump and yet another data set. And I keep on repeating this process and I keep on generating stump after stump. Alright, so this is the first stump that I have created. This will generate a new data set. Where in this new data set more, okay, hold on. Alright, sorry for the interruption. Uh, there was a power failure. Anyway, uh, yeah, that is what I was saying. We are going to create our first term, and based on how the first term performs, we are going to modify our data set, and using this modified data set, we are going to create a second term. And then based on how the second term performs, we are going to modify the data again, and that is how we are going to create the third stump. And this is how we are going to keep on repeatedly doing all this until and unless we have generated a number of stumps that we wanted to generate. All right, now each of the stump is going to have some weight associated with it. For example, this had, we calculated this had 0.97. So we said amount of say is the terminology we used to indicate weight. Alright, so each stump is going to have some amount of say. This stump had an amount of say of 0.97. In the same way, this will have some amount of say 0.4. This will have an amount of say 0.6, and this is what is going to happen. Alright, so this is what it is. Now, say I have created 6 stump. Alright, to do this classification of whether this person has heart disease or not. Now, this 6 term has this amount of say. Alright, and when I'm given some unknown data, I put this unknown data through this stump. I do the test. This each stump is going to do one single test, and then based on the outcome of the test, each stump is going to give me some yes or no result. Right. So, uh, what is going to be my final uh, output? Alright, what is going to be the output of the ensemble? So this is what I'm going to do. A few stumps are going to give yes as output. A few stumps are going to give no as output. Alright, as the classification output. Let us see the weight the amount of say of each of the stump. So yes is being given by this tree that had a amount of say 0.97, this stump that had a amount of say 0.32, this one that had a amount of say 0.78, and this stump that had a amount of say 0.63. All right, now uh, I have 0.97 plus 0.32 plus 0.78 plus 0.63. Alright, so I am going to add up all the amount of say of all the trees that are saying yes, and that is equal to 2.7. Alright, and I'm going to do the same thing with the stumps that are saying no. So these two stumps are saying no. Alright, and one of them has amount of say 0.81, the other has amount of say 0.82. Therefore, when I add them up, I get 1.23. The total amount of say of all the stumps that are saying no. The total amount of say of all the stumps that are saying yes is 2.7. So 2.7 is the greater of these two numbers. Out of these two, 2.7 is greater. Right? 2.7 is larger than 1.23. Therefore, I am going to say my prediction output. Alright, the output that the AdaBoost is going to give this algorithm is yes, because yes has a higher total amount of say. Alright, so this is how AdaBoost works. Alright, fine. So this is the boosting technique that we saw. Now this is the a piece of code to do AdaBoost. Alright. Once again, these 3 lines to load the libraries, loading iris dataset. This is the AdaBoost classifier with 100 different stumps, and then k-fold cross validation. Once again, 2 lines of code. Alright, very simple way to do AdaBoost using uh, sklearn library. Alright, now nothing much to discuss here. Just look at the code, copy the code into Colab and run it and see for yourself. Apply random forest as well, check different methods, see how good is it performing, and then try to do one thing. Instead of iris, check with some other dataset as well. Alright, now let us look at the final thing, that is stacking. Okay, so stacking is an ensemble learning technique that combines multiple classification or regression model via a meta classifier or meta regression. Okay, we will talk about what this means. The base level models are trained based on a complete training set. Then the meta model is trained on the output of the base level model. The base level will contain of different learning algorithm, and therefore stacking ensemble are often heterogeneous. Okay, this is a heterogeneous technique. Up till now we have been looking at homogeneous technique, right? So random forest had only decision tree classifier. uh, AdaBoost also uses the same concept of decision tree, but we do not grow into a full decision tree, we grow up to a stump. Then we saw boosting, a piece of code where we used only k nearest neighbor. Stacking, on the other hand, is going to have multiple base models. What does this mean? We have, say, this is my entire data set. Alright. Uh, I have many rows in this data set. I am going to do k-fold testing over here. Sorry, k-fold, in the way I do k-fold cross validation, in the same way I am going to split this. Okay. Now what I am going to do, I am going to take, say I am doing 5-fold split. Alright. I am going to take this 4 for my training. Alright, and what I am going to do is using this 80%, this 4 is going to give me 80% of the rows. Alright, this will be 20% of the row. Alright, so let me write 80%. Alright. Now what I'm going to do with this 80% rows is I'm going to train, say, a neural network, a SVM, and say a logistic regression. Alright. So I'm training different models on this 80% of the data. Alright. Then what I'm going to do, I'm going to take this 20%, okay, and I'm going to pass this 20% to this three models that I have trained on this 80%. Then say my neural network says that the output class is yes. My SVM says output class is no. On the first row of this 20%, on row 1, row 2, row 3, I'm going to have multiple rows, say row 5, row 6. Alright, so I'm going to have multiple rows. Right. So I'm going to take all these rows. Say here I have 6 rows. Okay. So I'm going to pass the first row through this neural network. Say neural network classifies that as yes. Then the first row through SBM. Say SBM classifies that as no. Then the first row through this logistic regression. Say this also says yes. Alright. And I'm going to see what is the actual target. Say actual target is yes. So I'm going to create this first row of this synthetic data set. So then I take the second row. Second row say this says no, and this says yes. Target is no. Alright. Then third row say this says no, this says yes, this says no, and this is say no. Alright. And in this way I am going to fill this data set for each and every one of this k fold, the fold that I left out. Alright. So this is how I create a new data set. This column contain all the output that I get out of the neural network that I trained on this 80% of the data. Alright. This column contain all the output of the SVM that I trained on the 80%, and this column contain the output of the logistic regression that I trained on this 80% of the data. Alright. And then this number of rows is equal to the number of rows that are in this fold that I left out. 6 in this example that I am showing. So this is how I create a new data set. Now what I am going to do is I am going to train a meta model. So this is either a meta classifier or a meta regression. So I am going to use this to train another model. Okay. Now the base level model are trained based on a complete training set. So this model are trained on a complete training set, that is my training set. So I have split it into test and validation set, right? So this is my test set, this is my train set, and this is my validation. I have split into train and validation. The base model are trained based on complete training set. Then the meta model is trained on the output of the base model as feature. Alright, so these are the output of the base model. These are the base model. This neural network, SVM, and logistic regression. So those are giving this output. This is the output of neural network. This is the output of SVM. This is the output of logistic regression. Alright. So this is the data set that I am going to train my meta model on. Alright. And then whatever output my later on I am going to use this architecture that I have created, alright, to do classification. Now how many models do I have? I have this one model, this one, and this one. Say in my example I have 3 models, alright, 3 base model, and I am going to have one meta model. Now say I am given some unknown, okay, data that I have to classify. What do? I pass it through my model 1, this neural network. I pass it through my model 2, this SVM, and I pass it through this model 3, this logistic regression. Okay, and this is going to give me some class, this is going to give me some class, and this is going to give me some class. So those I am going to put into one new column. Okay, and this new column I am going to put into my meta model, and my meta model is going to give me some classification output, and this is going to be my final output. Alright, so this is how stacking is done. Now stacking, we are not going to go deep into stacking. This is not a very complicated idea. Alright, this is once again a meta algorithm. This is not an algorithm, so there is nothing to go deep into. Alright, so the algorithms are over here, whether neural network, SVM, or logistic regression. These are algorithms that we did not study, or we could have used the algorithm that we did study, like decision tree, naive Bayes, or KNN. We are going to study all this algorithm by the end of this course. Alright, so this is what we have. Alright, we first use our base learner, and then the output of the base learner is going to be the row of a new synthetic data set, and then we train a meta model on this synthetic data set, and the output of this meta model is going to be our final classifier, right? And this is how we do this classification. We put this unknown data, we pass it through all this uh, base learner. The base learner is going to give us some uh, classification. We put those classification into one row, then we pass that row as the unknown data to our meta model. The meta model is going to now give us the final output. Alright, so this is stacking. Now stacking is if it sounds complicated, then read whatever is written here. It's not a very complicated idea. Just go back and watch the video from the portion where I started talking about stacking. Alright, stacking is very powerful. Believe me when I say that. In Kaggle competition, many competitions are won by stacking method. Okay. Now not only stacking, nowadays most of the competition are won using at least one form of ensemble method. Okay. Now, if you have to do good prediction, using only one model is a bad idea. So we have seen that using multiple model is a better way to do things. Here we have seen three techniques to do that: bagging, boosting, and stacking. So if you have to do classification or regression, instead of using just one models like we have been doing in our previous video, I would suggest that you do some ensemble technique. Alright, and ensemble technique is going to give you better result than uh, using only one technique. Alright, so this is what it is. In this video, we started by talking about what is ensemble method. Hold on. Yeah, we started off by talking about what is ensemble method. We saw the three types of doing ensemble method: bagging, boosting, and stacking. Then we looked at two different perspectives of classifying ensemble methods. One was into this sequential and parallel ensemble, and the other was based on type of base learner, that is homogeneous and heterogeneous ensemble. Alright. Then we looked at what is bagging. We looked at a code for to do bagging. Then we looked at what is random forest, and we looked at a code to do random forest. Then we talked about what is boosting. Alright. We talked about when is boosting the best technique and when is bagging better. Then we looked at a boosting technique known as AdaFruit. We solved AdaFruit, one problem with AdaFruit in details. We did one iteration of Adafruit in details, and then we ended up by creating the data set for the next iteration of Adafruit, AdaBoost. Okay, we did one iteration of AdaBoost, and we created the data set for the next iteration. Now we just have to repeat what we did in the previous iteration when we have to keep on doing that. Alright. Now we talked about how to use AdaBoost to do classification, And we looked at a small code segment that allows us to do AdaBoost. And finally, we ended today's video. We are ending today's video by talking about stacking. These are all the content for today's video. Uh, if you have any doubt, do feel free to reach out through WhatsApp, by mail, or by writing your doubts in the comment section below. Thank you for watching this video and see you in the next video.